Now we come to the second law, Newton's second law. I have a spring. Forget gravity for now, you can do this somewhere in outer space. This is the relaxed length of the spring, and I extend the spring. I extend it over a certain amount, certain distance, unimportant how much. And I know that when I do that, that there will be a pull, non-negotiable. I put a mass m1 here, and I measure the acceleration that this pull causes on this mass immediately after I release. I can measure that. So I measure an acceleration a1. Now I replace this object by mass m2, but the extension is the same. So the pull must be the same. The spring doesn't know what the mass is at the other end, right? So the pull is the same. I put m2 there, different mass, and I measure new acceleration a2. It is now an experimental fact that m1 a1 equals m2 a2. And this product, ma, we call the force. That is our definition of force. So the same pull on a 10 times larger mass would give a 10 times lower acceleration. The second law I will read to you. A force action on a body gives it an acceleration which is in the direction of the force. That's also important. Acceleration is in the direction of the force, and has a magnitude given by ma. Ma is the magnitude, and the direction is the direction of the force. And so now we will write this in all glorious detail. This is the second law by Newton. Perhaps the most important law in all of physics, but certainly in all of 801. F equals ma. The units of this force are kilograms times meters per second squared. In honor of the great man, we call that 1 Newton. Like the first law, the second law only holds in inertial reference frames. Can the second law be proven? No. Do we believe in it? Yes. Why do we believe in it? Because all experiments and all measurements within the uncertainty of the measurements are in agreement with the second law. Now you may object, and you may say, this is strange what you've been doing. How can you ever determine a mass if there is no force somewhere? Because if you want to determine the mass, maybe you put it on a scale. And when you put it on a scale to determine the mass, you make use of the gravitational force. So isn't that some kind of a circular argument that you're using? And the answer is no. I can be somewhere in outer space where there is no gravity. I have two pieces of cheese. They are identical in size. This is cheese without holes, by the way. They are identical in size. The sum of the two has double the mass of one. Mass is determined by how many molecules, how many atoms I have. I don't need gravity to have a relative scale of masses. So I can determine the relative scale of these masses without ever using a force. So this is a very legitimate way of checking up on the second law. Since all objects in this lecture hall and near Earth fall with the constant acceleration, which is g, we can write down that the gravitational force would be m times this acceleration g. I would normally write an a for it, but I make an exception now because of gravity. I call it gravitational force. And so you see that the gravitational force due to the Earth on a particular mass is linearly proportional with the mass. If the mass becomes 10 times larger, then the force due to gravity goes up by a factor of 10. Suppose I have here this softball in my hand in the reference frame of 26100, we will accept to be an inertial reference frame. It's not being accelerated in our reference frame. That means the force on it must be 0. So here is that ball. And we know if it has mass m, which in this case is about half a kilogram, that there must be a force here, mg, which is about 5 Newton for half a kilogram. But the net force is 0. Therefore, it is very clear that I, Valter Lyuin, must push up with a force from my hand onto the ball, which is about, of course, the same, which is exactly the same 5 newtons. Only now is there no acceleration. So I can write down that the force of Valter Lyuin plus the force of gravity equals 0. Because it's a one-dimensional problem, you could say that the force of Valter Lyuin equals minus mg. F equals ma. Notice that there is no statement made on velocity or speed. As long as you know f, and as long as you know m, a is uniquely specified. No information is needed on the speed. So that would mean, if we take gravity and an object was falling down with 5 meters per second, that the law would hold. If it would fall down with 5,000 meters per second, it would also hold. Will it always hold? No. Once your speed approaches the speed of light, then Newtonian mechanics no longer works. Then you have to use Einstein's theory of special relativity. So this is only valid as long as we have speeds that are substantially smaller, say, than the speed of light.